All right, I'm going to go ahead and start class. We're close enough. So remember, I'm giving you an exam on Wednesday so that you have an idea of how you did or whether or not you should drop the class on Friday, right? So I'm kind of stuck in a dilemma here. I was trying to figure out if there was a way that I could make this test part take home, part in class. So this was one idea I had. I wanted to just throw it out there. Come in on Wednesday, 10 to 16 problems. You do about half of them in class. The other half you take home. So that way you have a variety. If you get stuck on one, you can, look at something else, and hopefully half of them you'll know how to do that day. And then you'll have about 48 hours to take the others home and finish them and get them back to me. Of course, that means you have to be able to get here on Friday and, gas, car, whatever. But the only other option is everything you do Wednesday is the grade. And with the nature of these problems, I can only give you like 5 problems. I can only give you like one shell problem, one arc length problem, one surface area problem, one convergence test, like one example of each convergence test. So that's it. It's just like one of each, and good luck. So that's the other way to go. Um, the thing that sucks for this for me is that means you turn them in at 2. That means I have to grade them and tell you what your grade is within like an hour or two, like almost on the spot, which makes it hard for me. I'm trying to make your life a little bit easier.
Bring them in on like a Thursday though, right?
You can bring them in earlier, yeah. So what do y'all think?
Yeah, sounds good. This one.
Uh, okay. All right. So here, let's do this then. How about this? How about I'll be flexible with you as far as scanning and emailing them to me, but how about I make the deadline Thursday midnight?
How about for people that actually like they're on the halfway if they can drop this or not, and want to just hand it early, and everybody else like that they actually want to stay in this class, they like hand it on Friday.
What do you mean hand it in? You can hand it in anytime you want. It's just there has to be a deadline. There has to be a deadline. That's all.
I'm just saying like they can do it on Friday, and everybody else can turn in early, and once you know the grades, they decide right
Oh,
there.
I see what you're saying. I see what you're saying. Yeah, I like that idea. I like that idea. How about this? If you are going to want to know what your grade is so you can determine if you're going to drop the class or not, then you got to have it to be by Thursday midnight. Thursday midnight.
So that way you could just go ahead and like grade those people.
That's right. I can take care of that. If you want to scan it, email it, that's fine. But you can't take a picture on your phone and send that to me. It needs to be a good quality scan, something I can just open up in an email. Don't send it as a text message. Email, PDF, or something like that, JPEG, something I can just print and go. All right? Okay, so let's do that. We'll make that official then. Thursday, midnight. If you want to know, if you want to know
Thursday midnight for early grading.
grade by Friday. All right. Everyone else, it's Friday, 2 p.m. Same thing. I'll let you scan it and email it to me, okay? That'll be the plan.
I'll bring stuff here. Whatever.
So what you're going to see then on this test is probably a good mixture. There will probably be, 2 shell problems. There will probably be 2 arc length problems, 2 surface area problems. So 2 of each, a little bit of variety. That way, if there's one that you're better than the other, you can knock those out, and then take the rest home. Of course, I'll give instructions on Wednesday. I mean, the take-home portion, you're not supposed to work with other people, blah, 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 all that stuff. So, okay, that's the plan then. Subject to change at my discretion. Okay, that's my little star at the bottom that it's very fine print, you can't read it. It's so fine you can't read it. All right. I'm not like I like take-home exams, but I don't know. I just don't like other people's doing other people's work. Um, Anybody gonna take Cal 3 with me? Maybe after this experience, maybe not. But um, huh?
Are you teaching it? When are you offering
Oh, I don't know. Whenever I usually teach it in the fall.
You're teaching it.
But look, like in my Cal 3 classes, we have 10 mini exams. That's what they do. All take home, 10 mini exams. Everything is, it's almost an exam every other week. And people are always like, yes, take home. And then you realize that yeah, the take home, it still weeds out the people who can't do it because these take homes are monsters. Um, anyway, no, monsters is in time consuming but there's no other way to do it. All right, we're ready to move on. This is our last lecture before the test, and there's quite a bit of information here. 8.4. I've put the answers up for everything up through 8.3, worked out by hand, odd problems. Has anyone opened those up and looked at those yet? Yeah, I know at least two people have. Um, so hopefully that's helping you. If not, oh well. So now I'm going to do 8.4. This will be on the test. All right, 8.4 will be on the test. And what I have for you also at the end here is a handout. It's called Strategy for Testing Series. And you'll be allowed to use this on the test along with this thing. Okay, that too. No. You can have your own cheat sheet. That's fine also. Yes. You can always have that, but these also. We'll talk about that in a minute. Okay, let's move through this. So in 8.4, we're going to talk about some other convergence tests. Remember that up to this point, if you go back and look at the convergence tests that we've done so far, all the series that we've been talking about are positive series. So that means that each term of the series was a positive number. Okay? Everything in 8.3 were positive tests for positive series. Now we want to look at how can we do tests on series that have negative terms in them also. So the first test we have, and maybe I should ask you real quick, what are the tests from 8.3? Integral test? Okay. Comparison test? Well, a p-series is a type of series. We know if it converges or diverges. I don't know if you could call it a test because it either is or isn't. But yes, p-series we should know. Geometric series we should know. Okay, comparison, integral test, limit comparison test, and the one that you should always start pretty much almost every problem with, the nth term test for divergence, basically. So those are the tests that we have from 8.3. Now we're going to look at some new tests. Alternate series test. Let's see if this will all fit on here. I think that's okay. Okay, so the alternating series test. So it says, let's say that you have a series that alternates. Okay, positive, negative, positive, negative, positive, negative, positive, negative, or it could be negative, positive, negative, positive. It doesn't have to start positive. Okay, as long as they alternate, every term alternates. Then look at these two conditions I have written down in red here. Get back here. Okay, if b sub n plus 1 is less than b sub n, an upside down A means for all n. I'm not making that up. That's like a mathematical symbol. All right, we use it. So remember that in a series, the negative 1 to the n minus 1 created the alternating, right? That just made your signs flip around. And then the rest of it is the rest of the sequence, right? So this part right here, what we're saying right here is look at everything that doesn't have the alternating part in it. So take the sign out, the thing that switches the sign back and forth, and just look at this piece. If this is true, that's the first thing we need. What does this mean? B sub n plus 1 less than B sub n. What kind of sequence is it? The n plus 1 term is smaller than or equal to the one before it.
The one that came in?
So let's say this is B sub n, right? Here's the x-axis or something. Here's B sub n. B sub n plus 1 has to be what? Smaller or equal to it. So it's got to be below or equal, right? So this means that as you go out into the sequence, each term is getting smaller or they're all staying the same, right? Yes? That's the first thing. And let's say that your sequence goes to 0. So that means that these are all getting smaller or possibly staying the same, right? And they're headed to 0. Then the conclusion is that the series converges.
Even though the other one's going to be bigger?
Well, it may alternate, right? So I'm going to draw a picture real quick. Imagine you have a series where this one starts out here, right? Let's just say this is the x-axis. The next one has to be equal to it or smaller, right? But it's going to change signs. So instead of being up there, it's going to be maybe down here. And it keeps oscillating up and down, but where's it headed? To 0, right? So what happens is it has to, well, that means that the sequence converges, right? The sequence converges. The series, though, will also converge. That means if you add them up, it'll converge. So that's the conclusion of this test. Now, I'm not here to prove why it's true. Okay, the book does the proof if you want to look at it. But this just says if your sequence is going like this, that means when you add them all up, it'll converge. You have to be careful because that's not what we said last class. Like with positive series, remember with positive series, just because the sequence goes to 0 didn't mean it converges, right? That was inconclusive, right? If your sequence goes to 0, that's inconclusive with positive series. But with alternating series, that actually tells you something. It tells you it converges as long as this is true, though. Okay, so let's look at this first series here. 1 minus a half plus a third minus a fourth plus a fifth. Y'all recognize this series? Harmonic, except harmonic didn't alternate, did it? Right? Harmonic didn't alternate. Now, what does a harmonic do? If they're all pluses, what does harmonic series do? Diverges, right? Diverges. So it diverges, right? But this isn't harmonic, it's an alternating harmonic. So I wonder if it converges or diverges. Well, let's look at it. First of all, can we all agree you could rewrite the series this way? N equals 1 to infinity, negative 1 to the n minus 1. If I plug in 1, my first term is going to be what? If I plug in 1, 1 minus 1 is 0. Anything to the 0 would be 1, wouldn't it? So I would get a positive 1 and then 1 over 1, which gives me 1. So my first term is positive. Then I plug in 2 in there, you'll get a negative 1 over 2, that's negative 1/2. And then I keep going. So is that all right that this is my series? Okay, if that's my series, then the B sub n part, that means that's the part that does not involve the changing of the sign. So that's my B sub n, right? The 1 over n. So that's what I wrote right here. B sub n equals 1 over n. Now what I need to do is take a look at that and see if both of those conditions are met. So the first thing I'm checking is this first condition. Is B sub n plus 1 less than or equal to B sub n for all n? So I plug in n plus 1 into my sequence, and I plug in n, and that gives me these two pieces here. Is that all right? I'll erase that because that looks terrible. All right, but that gives me these two pieces. Is this true? How can you tell it's true? Yeah, the fraction on the left side is smaller than the one on the right because the denominator on the left is bigger than the one on the right. Right? Now this is true if only when n is bigger than 1, right? Like we know that only because you're only allowed to let n be 1, 2, 3, 4. If n's allowed to be any number, that's not always true. Okay, so the first condition is met, right? Second condition, is the limit as I go to infinity 0? So I just look at my b sub n, it's 1 over n. That limit went to 0, doesn't it? So both conditions are met. This series converges. So harmonic, where it's all positive, that diverges. Oscillating, alternating harmonic converges when you add them all up. Questions? I'm sorry? No, we don't know what it converges to.
You don't need to know?
We can't figure it out. Okay, in general, it's very difficult to figure out what series, bless you, what series converge or diverge to. In fact, this section talks about a way to estimate it. I'm going to skip it completely, how to estimate it. If it's a geometric series, you can tell me what it converges to. That's pretty much it, right? Sometimes the collapsing telescopic ones, you can tell me what it converges to, but
When you add them all up, yeah.
when you add it all up, yeah, remember, because that's what the telescopic, the inside canceled out, and you're left with the two ends, and then you let the n go to infinity, and you usually got a number. But other than those, really, it's hard to figure out what a series actually adds up to be. So all we want to know is if it converges or diverges. Okay, the next problem. I think it's the next problem. Let's see. Yeah, I just say that at the end there. Notice, and look at this notation. You'll see me do this a lot within my notes. This means the sum n equals 1 to infinity. But instead of writing it over and over, I just do the sum. And it's not me being lazy, well, kind of, but the book does it too. This is kind of like we understand that there's an n equals 1 to infinity because that's what we keep doing over and over. So that represents that infinite sum, okay? And so this is, we're saying that that one was harmonic, but when you alternate it, it converges. Let's take a look at this one. First of all, is it an alternating series? Is this alternating? Yes, because you have the negative 1 to the n plus 1, right? So you could start writing out some terms. As soon as I see it's alternating, I'm just going to go for this right now. I'm going to just try and see if the alternating series test works, if I can get both conditions to be met. So the first thing I'm looking at is this true? So when you're looking at b sub n plus 1, we all understand that b sub n is that piece just to the outside without the negative 1 on it? Right? Without the negative 1 to the n plus 1, it's just that other piece. That's your b sub n.
So you're just replacing n plus 1 for the n.
That's right. That's what I want to make sure you understand. All I'm doing is going in here. B sub n plus 1 means come into this and replace your n's with n plus 1's. So it becomes n plus 1 squared over n plus 1 cubed plus 1. So that's just substituting in. And then b sub n is just, well, it's just that, b sub n. And now what you need to do is show that this is true. So what did I do here? No, I'm not taking a limit or anything here. I did a multiplication on both sides. First by n cubed plus 1. So I came in here like n cubed plus 1 on this side. And did I say n cubed plus 1? Yeah, it is n cubed plus 1. Like that. I did that on both sides. The n cubed plus 1 cancels here. And it turns into this on the left, right? But what happened to the denominator here? I multiply both sides by this denominator here and over there, right? So it's almost like cross multiplication. I'm clearing fractions and I create this new inequality. Is that all right?
Yes.
Anyone, sure? Anyone have a question on where I got that?
I don't
Look, if I have x over y equals a over b, I can multiply both sides by b. cancels. I get bx over y equals a. Then I can multiply both sides by y. The y's cancel.
So like, but when you went down, where did the n plus one that's being cubed go?
Over there on the other side now.
It's on the other side now.
Yeah, it's right here.
So you pretty much found a common denominator. No, the other one. It's
Well,
talking
but
about
like the one that's on top of
n
it.
plus 1 cubed, right?
This right here
Yes.
is going to multiply times that, so it's right here.
Oh, okay.
You found the common denominator.
I found a common denominator and multiplied both sides by that common denominator. Yeah. And then from there, I just like multiplied that all out. And when I multiplied this all out and expanded everything, I mean, I had to take my time through this, okay? I had to figure out, what's n plus 1 cubed. I had to, that turns into all this right here. And then I distribute my n squared through, collect all like terms, things cancel. And I finally get to, at the very end, this right here. Well, actually, I get to the line above it. And then from here, I factor out an n squared. And why is that true? Why is the right side bigger than the left side?
So right now has the left side component and more.
What's the smallest n can be? 1. So the smallest the n squared could be, it'd be 1, right? And then here, 1. So if I take 2n plus 1, I add 1 to it, right? And then multiply it by 1, it's still bigger than just 2n plus 1. So this is true. So I know, first of all, that it's basically decreasing, right? That each term is smaller than the one before it, or equal to it. That's the first condition I need to show, right? What's the next condition? Oh, yeah, hold on. The book points out also that you could have taken the sequence, remember it was n squared over n cubed plus 1? And you could have looked at it as a function of x, taken the derivative, which is quotient rule, and at the very end you could have determined that the derivative is always negative. If the derivative of something is negative, what does that mean? It's going down, it's decreasing, right? So if the function decreases, then the sequence must decrease also. So you could do it either way, okay? This way, I mean, it just depends on how comfortable you feel. I think the book did it this way, like this, showing the derivative. I did it the other way just to give you some variety of different ways you could approach the problem. Any questions? I'm not done, right? I still have to show the limit as n goes to infinity of the sequence is 0, which is pretty clean, right? That's not a whole lot of work there. That's your sequence. Let n go to infinity, you get infinity over infinity. Basically, this can turn into a L'Hopital, and you could get 0. So that means it converges. How about this one? Is this convergent? Don't worry, I'm going to work some out at the end here. Right now, I'm just going through some examples, seeing if you can follow the work, and then we'll get our hands dirty with some. First thing that should stick out to you, it's alternating, right? It's alternating. Then I look at what's the b sub n? 1 over n factorial, right? That's my b sub n. I want to know if b sub n plus 1 is less than b sub n. Is this true? Yes. And you can show it this way also. Remember, n plus 1 factorial means n plus 1 times n minus 1. It keeps going down. Or you can write n plus 1 factorial as n plus 1 times n factorial. Does everyone see how that works? Because this comes up a lot.
I don't see the difference.
Okay, I'll do it on the board. Or no, I won't do it on the board. Look at if I write 5 factorial, that means 5 times 4 times 3 times 2 times 1, right? Or I could write 5 factorial as 5 times 4 factorial, because that means 5 times 4 times 3 times 2 times 1, right? So now if I write n plus 1 factorial, that means n plus 1 times n times n minus 1, and I keep going down, right? Or I could write n plus 1 times n factorial. That would give me the n plus 1 here, and then n factorial would mean n minus 1 the rest of the way. That makes sense? Let's see if it does with this example.
Where you peel it off?
Yeah, you're peeling it off basically. How could I write n plus 3 factorial where it has an n factorial in it? How could I rewrite that where it has n factorial? N plus 3 times n plus 2 times n plus 1 times n factorial. See, those are the same? That one, I peeled off the first 3 factors, and then from n on, I wrote it as n factorial. Does that help? Does that make a little more sense? Okay. So now, on this one, what I've done, n plus 1 factorial, I wrote it as n plus 1 times n factorial. So you can clearly see that this denominator is bigger, right, than this denominator, which means this fraction is smaller than that one. Yes?
Yes.
And therefore that inequality is true. And, oh, well, actually I multiply both sides by n factorial. N factorial, and I got that. And that's obviously true, right? Yes. But what?
She had a question.
Oh, you had a question?
I was saying, like, whenever you do that, you're always trying to get n factorial, like, just when you
Well,
do the
not always. I was trying to get it to n factorial because I had n factorial over here. So I was trying to get something to compare it to. That's it. As we'll see, I don't know today, but we'll see as we go on. Sometimes it won't be n factorial we're trying to get it to. It might be something else. Okay, so the first condition is met, right? The second condition we need for convergence, as the limit as n goes to infinity, this is true. Is that obvious to you? That goes to 0, right? You don't even need to do it by L'Hopital's rule or anything like that. I mean, you've got a fixed number over something that's getting infinitely large, that's going to converge to 0. So that's it. That thing converges. So do you see, remember last class, we said, and this was the quiz question, right? If the sequence goes to 0, does the series converge? If the sequence goes to 0, does the series converge? Yes or no? True or false? If the sequence goes to 0, does the series converge?
No.
I even handed your quiz back to you. What is it? If a sequence goes to 0, if a sub n goes to 0, does that imply that the sum of that sequence converges? No. No.
The graph would go like this, right?
It
And
could-
just follow the points.
It could do a lot of things, but harmonic. Harmonic, each of the pieces is getting smaller. You add them up, it goes to infinity. That's what happens with normal sequences in series, the way we've been doing it so far. Today, we're almost saying this is true, right? We're saying if the limit of the sequence goes to 0, it converges, but what are the 2 other things I had to have? I had to have this condition that the one before it's smaller than the one in front, right? The next one is always smaller than the one before it, and has to be alternating. Okay? So keep that in mind. Okay, absolute convergence. Now this is not a test, this is a definition, okay? The alternating series test was what we just did 2 examples or 3 examples of. Now this is a definition. What does absolute convergence mean? So let's say we have a series, okay, you're adding up a bunch of stuff. It is said to be absolutely convergent if the series of the absolute values converges. So whatever's happening here, doesn't matter if it's alternating or not, who cares? If you take the absolute value and the absolute value of that series converges, then it is said to be absolutely convergent. And I put a note here. Note, be careful. The original series need not be convergent, okay? You can have a series that doesn't converge that is absolutely convergent. And I'm going to show you an example in a second, all right? All absolute convergence means is that when you take the absolute value and look at that new series, you get convergence, okay? Let's look at this one. All right, do y'all recognize this one? We just did this. Just take that n, forget that n here, and just put it on the outside, 1 over n. Isn't that harmonic alternating? What did we see earlier, just a second ago? That converged, right? The alternating harmonic converged, right? Yes? No? Yes? Okay, the alternating harmonic series converges from what we did before. However, if we take the absolute value of this, right, take the absolute value, it kills off the alternating, doesn't it? Because it makes all the negative ones turn into positive ones. So instead of being just alternating harmonic, it's just harmonic, right? And that diverges, right? You see what I'm saying here? This series right here converged, but it does not converge absolutely. This converges, but not absolute. People always think like absolute convergence means like the greatest type of convergence. It is absolute. No, absolute just means absolute value. That's all it means, okay? So this series converges, but is not absolutely convergent. So when you take its absolute value, it doesn't converge, okay? I know, you know what I mean by the word absolute? A lot of people kind of mistake it for like meaning something like the ultimate type of convergence. It's not. But we do have this theorem, okay? It says if a series converges, well, hold on, here's the theorem. If a series converges, right? So let's say we take some series that converges, and we take its absolute value and it diverges. Isn't that what just happened? We had the alternating harmonic, it converged. We took the absolute value, became harmonic, it diverged. Then the series that we started with is called conditionally convergent. So it converges, on its own it converges, right? But absolutely it does not, so it's conditionally convergent. This is all just definition stuff. All right, next one. If the absolute value of a series, right? Absolute value here of each of the terms. If that series converges, so isn't that absolute convergence? Right? The absolute value of all the terms, that's absolute. If that converges, that's called absolute convergence. Then the series itself, without the absolute value, converges. Is this starting to get mind-boggling a little bit? Didn't we just say the other way didn't work? Hold on. What? What the hell's happening here? If it converges absolutely, then it must converge. Absolute convergence implies convergence. Are you thoroughly confused yet or not? What do you like, art more or the this is a little better than art? Okay. Okay, let me what happened with that harmonic? Because the one I was showing you with harmonic, I think, is probably what's confusing you. I meant for it to confuse you because I want you to think about this. Okay. The alternating harmonic converged, right? And when you took the absolute value, it diverged. So just because you converge, just because if this guy, if that converges, does that mean that that must converge? No, not necessarily. It may diverge. This theorem says if this converges, that's guaranteed to converge. Guaranteed. The other way. So I think there's a way you can rationalize this. If I sit here and I say, look, I've got some series here, right? and I'm going to take the absolute value of each of the terms and add that up. Isn't that going to be like a positive number plus a positive number plus a positive number forever? Yes? And we've seen before that this could converge, right? So let's say it converges. That's what this theorem is saying. Let's say when you add up all the absolute values, it converges. Now, look at this series without the absolute value. No, this theorem says what? It has to converge. Here's why. If all of the terms considered to be positive added up to be a number, then if you take it and maybe you make this one instead of the positive, change that to negative, make that one, positive, but then the next one negative, this quantity has to be less than this one. Because this is all positives, this is positives, and possibly some negatives. So if that one goes somewhere, the one below it has to also, because it's kind of bounded by that one. Okay, that's what that theorem says. But the order is important. Convergence does not imply absolute convergence. Absolute convergence implies convergence. Okay? Whew. Absolute convergence implies convergence. Convergence does not imply absolute convergence. So in that sense, it almost is like absolute convergence, right? Absolute convergence implies convergence. So here's an example. All right, does this series converge or not? So we've got sine n over n cubed. This series is not alternating, right? It's not an alternating series, is it? Does it, because alternating means the first term's positive, the next one's negative, then positive, then negative, then positive, then negative, or you start negative, then positive. This one, it's kind of weird because sine, we know sine changes, right? Sometimes it's positive, sometimes it's negative. If you were to plot these points of this sequence, if you were to plot them out, some of them would be positive and negative, and they would switch. Sometimes there would be like 2 positives in a row, and then like 3 negatives in a row, and then like maybe 1 positive and 2. It just depends on where you are in the sequence. But it's not alternating. So we cannot do an alternating series test, right? Cannot do it. But what I am going to do, and this is very powerful now for us, is I'm going to take the absolute value of the sequence. Because if the absolute value of the sequence converges, I don't have it written here, but if the absolute value of the sequence converges, what happens? The regular one converges. So that's a major result today. If this converges, then this converges. Hey, if this diverges, does this diverge? Maybe, maybe not. If it did, it would be an if and only. If that was true, they would have made it an if and only if, because the implication would have worked both ways, and you can do logical tests to show that you could take negations and it would be the same thing. Yes?
Can you do the squeeze theorem on this problem?
I don't know. Can you? Let's see. I think that's exactly what happened here. Well, you can do it several ways. You could do squeeze theorem. I definitely used kind of a squeeze theorem tactic here because when you take the absolute value of this, you know that your numerator, right? Your numerator, the sine function, if you take the absolute value of it, has to be lower than 1 and bigger than 0, right? Sine by itself is between negative 1 and 1, but the absolute value of sine is between 0 and 1, yes? So this right here is definitely smaller than having a 1 up there, and n cubed, just leave it alone. Do y'all agree with this inequality? 1 is bigger than sine of n. So 1 over n cubed is bigger than sine n over n cubed, absolute value. And then this is a p series. So what am I using here from last class? When I do this and I take two things and I compare them, right? It's a comparison test is what I'm doing. I've shown that my series is always below another one, and that series, when I add them up, it's a p series, and a p series with p3 does what? Converges, right? So if 1 over n cubed added up, I didn't put the adding them up forever, but if I add all these up on the right side and add all these up on the left, whatever this adds up to be is bigger than whatever this adds up to be. That adds up to be a number because it converges. That means that converges. Yes? And if the absolute value of that sequence or that series converges, what? Well, then without the absolute value converges because of that theorem. What do you think? Come on, tell me how you feel. What's up?
So on most of these, you just do the absolute value, and if it converges,
Yep.
and then if it doesn't, then you have.
Yeah, if it doesn't, then you're going to have to do something else. But the trouble would be here. I mean, we relied in this problem on getting some control over this, right? So we used a comparison. That may not be something we can use later. Just every problem is unique. We'll see. Like I said, I have a handout, a strategy for these things. And one of the things it'll say in here is that there is no cookie cutter for each one. But this is a good thing to try.
In this equation right here, it's limited because of the sign of it. So you're not changing the bottom at all.
Nope, not changing the bottom.
Need to, 'cause
There's
it's
no need to.
limited.
That's right.
So instead, you're just killing off that sign of it and turning it into 1.
Yep,
Because it's already absolute 0 1.
that's right. See,
1's as big as it can get.
that 1 is the biggest it could be. Remember when you have a fraction, if you're comparing a fraction to another fraction, and you want your other fraction over to the right of it to be bigger, you can pick something where your numerator is smaller, or where your denominator is smaller, or your numerator is bigger. And in this case, I picked something where this is a fraction where my numerator is bigger than or equal to this. So that means the fraction must be bigger than or equal to it. All right, so we've got alternating series test. We have the idea of absolute convergence. We have the idea of conditional convergence. We have that if something converges absolutely, it must converge, right? And now we have another test. This is the second to last test. So we have one more test after this. This is called the ratio test. All right, the ratio test says this. Let's start out with the series. If you take the limit as n goes to infinity of not just the sequence in here, you're not looking at just a sub n. What are you looking at? The ratio of a sub n plus 1 over a sub n. Isn't that the term right after this one? Right? A sub n is this term, a sub n plus 1 is the next one. So what you're doing is you're looking at the ratio of those two terms, the absolute value of those. If that limit gives you a number L, and that number L is less than 1, this series is absolutely convergent. And absolute convergence implies convergence, doesn't it? So this is Big Daddy. I mean, this is the big time right here. If it converges absolutely, it converges. So that's a very strong form of convergence, isn't it? All right. That's if that limit turns out to be a number less than 1. Now, if it turns out to be a limit, if this limit turns out to be a number greater than 1, then it's divergent. Okay? And if the limit turns out to be 1, the test is inconclusive. Then you're screwed. You have to try something else. Yep. Now the ratio test, these problems, this is a very, very powerful test. The algebra inside of these can get a little bit complicated, but I think once you do a couple, you kind of get the hang of it. All right, so first thing, here is an alternating series, right? Alternating series. I could try the alternating series test, couldn't I? That means I would look at the end of this, the n squared over 4 to the n, and I could check what conditions? What's alternating series test?
B of n plus 1 is
Less than b of n. Okay, that one. And then I would also see if the limit of this one goes to what? 0, which it does. The hard part might be the showing that the one b sub n plus 1 is less than b sub n. That might be hard. But in any event, that's one way you could try it. I'm going to do this ratio test just so you can see it being used. All right? So this is a sub n, right? This is the part, yeah. Look at a sub n is the whole thing, okay? Right there. Now, I'm going to take that and look at a sub n plus 1 over a sub n in absolute values. So I first plug n plus 1 into this. Negative 1 to the n plus 1, n squared becomes n plus 1 squared, over 4n becomes 4n to the 4 to the n plus 1. So does everyone see that right there is a sub n plus 1? Then this is what? A sub n, absolute value. I want to know what happens as n goes to infinity. If that's smaller than 1, this converges. If it's bigger than 1, it diverges. If it is 1, scratch it out, try something else. Okay, so let's see if you can follow what I do on this next step. And I'll leave the first one up there a little bit. So I have a fraction over a fraction, right? Anytime I have fractions over fractions, I like to flip the fraction up into the side. So I like to always take like this fraction and flip it. So see it flipped right here? And put them side by side. Now I canceled out the negative 1 to the n plus 1 and the negative 1 to the n. Now don't mistake this. I didn't cancel them with each other. I just got rid of them. Why did I get rid of them?
Negative times negative, right?
It's because I'm going to be taking an absolute value. So it doesn't matter if I get a negative 1 or a positive 1 out of that. At the end of the day, when I absolute value it, it's done, isn't it? So I got rid of those. So I think what I'll do is I'll put this one in yellow and this one in blue. Well, that ain't blue. So just they're gone because of the absolute value. All right. Now, next thing. What did I do here? What did I do from here to here?
You separated the 4 and plus
There we go. This 4 to the n plus 1, I rewrote it as 4 to the n times 4 to the 1, right? Because you would have, if this was a 1 right here, you put them together, that'd be 4 to the n plus 1. Now the reason I did that is so I could cancel it with that 4 to the n up there. So those now do cancel, don't they? And this now, I can get rid of the absolute value because everything there is positive. So I get that. And then I expand out the numerator, so I FOIL that out, right? N squared plus 2n plus 1. And now I let n go to infinity. And when I go to infinity, I get infinity over infinity, don't I? So what would you use if you have infinity over L'Hopital? And then you'd probably have to do L'Hopital again, or maybe not. Yeah, you'd have to do L'Hopital again. And then you'd get 1/4. And that is less than 1. And so it converges. In fact, I put it converges, but absolutely also. I mean, it's actually absolutely convergent, which means it's convergent. So that converges. Would it have been easier to do alternating series test? Maybe. Maybe. It just depends on what, are you going to pick, what tool are you going to use when it comes to the test, right? Are you going to pick the aluminum bat? Or are you going to take the wooden bat? You know what I'm saying? Like, you're going to have different things. They both may work for what you need. Look at this one. This series, is it alternating? No, so I wouldn't even consider the alternating series test, would I? Eventually, I stumble upon trying the ratio test. Okay, that's what I'm going to try. So I first identify what the sequence is. Then I have to plug in n plus 1 into this, right? So I plug in n plus 1. It's n plus 1 to the n plus 1 over n plus 1 factorial over that thing, right? N to the n over n factorial. And then I say I always wind up flipping that up, like flipping it. So usually when I do ratio test, I don't even show that a sub n plus 1 over a sub n. I go automatically to this. Like I take the first piece and flip the other one and put it next to it.
Then you're gonna peel up from the bottom.
Yeah, very good. I'm going to take the factorial and peel one off. When I peel that one off, it's going to cancel with this n factorial here. And then this n plus 1 to the n plus 1 means n plus 1 to the n times n plus 1 to the 1. So that's where this one comes. Do y'all see where all this is coming from or not? I'm trying to get things in common to cancel. And so I get real nice cancellation in here. This is this, n factorial, n factorial. Then I get this over this, which looks like that might be bad. It actually is kind of bad. I'm gonna give away the answer, but okay. So all I have left is n plus 1 to the n over n to the n. They both have the same exponent, n. They're both raised to the n, so I can put n plus 1 over n to the n. Any questions on up to that point right there? Okay, now the next line, what's 1 plus 1 over n? Where'd that come from?
N over n plus 1 over n.
Yeah, just split that into two fractions, right? N over n is 1 plus 1 over n. Now I say that this is equal to e. What the hell? So let me remind you why that's e. I'm going to call, let's just call it L is equal to the limit n goes to infinity of 1 plus 1 over n to the n. That's what I'm trying to figure out, right? That limit up there is this piece right here that turns out to be e, doesn't it? This is a Cal 1 problem. Yes, you can take the natural log on both sides. Natural log of L equals limit n goes to infinity of natural log of 1 plus 1 over n to the n. Now the reason why we come in with natural log on both sides is because here with this natural log you can take that power and put it out in front. How many of you saw this with L'Hopital in Cal 1? Maybe. If you took me, you saw it. You may not remember, but you did. N natural log 1 plus 1 over n. Now, I got kind of ahead of myself here. I never even talked about why this limit is something we have to do all this for. What does this want to become right here? What's 1 over n? It wants to become 0. What's 1 plus 0? It's 1. So the base right here, the base of this wants to become 1, right? But it's not. It's always a little bit bigger than 1. And then what does the exponent want to become? Infinity. This is known as an indeterminate form. Something that wants to be 1, and the power wants to make it bigger, and then they fight with each other, and eventually they compromise and say, we'll just be e. All right? But this is the compromise. This is what they're doing. So take your limit right now. At this point, let n go to infinity. 1 over infinity is what? 0. 1 plus 0 is 1. Natural log of 1 is 0, right? So this guy wants to be 0. And this guy right here in front, the n that I had pulled out as a power, wants to become infinite. That's still an indeterminate form. Infinity times 0. Huge number times very, very small number. Who wins? So they continue to battle. They still can't decide. So now what I do, anytime you have infinity times 0, you can always take one of these and drop it into the denominator. So I take my n out front. Watch what I do with it. I rewrite it as a 1 over n on the bottom. So that n on top is the same as a 1 over n on the bottom, because that would flip up and become an n. But now when you take your limit, where does the numerator go? Where does this piece go?
0.
Natural log of 1, which is 0, over, now where does 1 over n go?
0 also.
Goes to 0 also. Now you have 0 over 0, so what can you do? L'Hopital's rule. I'm running out of room. Natural log of L equals, by L'Hopital's rule, limit n goes to infinity. The derivative of the top.
1 over 1 plus
1 over, right, 1 over whatever's inside times the derivative of what's inside, which is negative 1 over n squared. I'm not going to go through that. But that's the derivative of 1 over n is negative 1 over n squared. And then the bottom, derivative of bottom,
n to negative 1, right?
n to negative 1, so negative 1 over n squared again. And these cancel. So all you're left with is this. So what happens as n goes to infinity now? This approaches 0, 1, so this is all 1, right? So you get the left side, which says, I'm going to have to do it down here, natural log of L equals 1. So take E on both sides. So natural log of L equals 1. E of natural log of L is L. L equals e to the 1, which is E. So this limit is E. All right, so what's the conclusion of all this, though? That E is what, 2.718 something, right? It's bigger than 1. So this series diverges. If the ratio test spits out a number bigger than 1, you diverge. Last test of the day. The root test. The root test is very similar to the ratio test in the sense that you're going to be taking a limit. If it's less than 1, you get convergence. If it's greater than 1, you get divergence. If it is 1, you don't know anything. Okay, so in that sense, it's just like the ratio test. The only difference is you're not going to be taking the limit of a ratio. You're going to be taking the limit of a root. So what you do here is you take the limit as n goes to infinity of the absolute value of your sequence, but the nth root of it. That's it. So you don't have to do an n plus 1 or anything like that. So here's an example. Sum n equals 1 to infinity of 5n plus 1 over 11n minus 1, all raised to the n. Is it an alternating series? No. So no alternating series test. Could we do the ratio test? I mean, could you plug n plus 1 into all those and do a ratio? You could. But the thing that's really leading me to the root test is the fact that the whole thing's raised to the what? The n. And doesn't the root test have an nth root in it? Doesn't it? So what I do first is identify the sequence, and then I apply this limit. I want to take the limit as n goes to infinity of the nth root of a sub n, absolute value of a sub n. So that's the nth root of all of this to the nth power. The nth root and n cancel, don't they? So you get just the limit of the inside. And why is that 5 over 11? L'Hopital will get you there, right? Infinity over infinity. L'Hopital would get you here. Then you got less than 1, you're in business. It's not square root, it's the nth root of n.
So it'd be like 1/3 over 3.
Yeah, they exactly wipe each other out.
It would become 1.
It's when you do this, the nth root of x to the n, you get x. So they kill each other off. That's why when we look at this problem, when we see that n up here, everything's being raised to the n, we're like, aha.
That's like
Root test for sure on this. Yeah.
because you have like 1 over n and then n over 1, and then when you multiply by 1.
So what happens if 5 over 11 is smaller than 1? It converges, right? Okay. I think that's the last one. Yeah, there we go. That's your homework assignment.
Is this going to be on the test as well?
Yes. Everything through 8-4. Look at that, it's not even 2 o'clock.
Yes.
We're done with everything that's going to be on the test. So this says 3 through 11 odd. And it says on 9 and 11, if you read the book, it says to find like the error or something like that. I said I'm not going to show you that formula. So all I want you to do on 9 and 11 is just show that they converge. They do converge, but just show it. And then 19 through 39 odd is just a random mix of, could be alternating series test, could be absolute convergence, could be root test, ratio test. Go ahead.
When should these be posted? When will we find these posted?
Well, I'm going to try and get these out. I haven't started these yet, but what I do have is now this handout. I think you're going to like this handout. I think you're going to like it. I'm feeling good about it.
I like to read. Do you have this on the interwebs?
The what?
The summary of convergence test on the interwebs?
This thing, I actually did put it on our website, Canvas. I don't know if I put that one out there. What I'm handing you right now, I did put on our Canvas shell in case you lose it. It's under Files, but it's just sitting right under Files. It's not under Solutions or anything like that. It's just sitting there. I think it's called Series Summary. That should be enough for all of you.
Have that one extra page of,
There we go.
the notes.
We got an extra.
Yeah, let's talk about it. Hold on. All right, so I'm not going to read through this word by word, but let's see what they have to say. This was actually taken from the author of the book's website. Basically, he's just saying that when it comes to trying to, come up with a strategy, it's like integration. There's not like a cookie cutter way of doing it. And I've helped a couple of students in my office on these. And when we only had like the first two tests, when we only had like integral test in comparison, when those were the only two, it was almost you could be systematic. Like, does integral work? Let's see. Okay, no, comparison. But now that you have all these tests, right? All of these tests, you don't want to go through and say, let me try this one, then this one, then this one, then this one, this one, this one, because that could take you forever. You want to try to start to get some instinct to these things, kind of like with integrals, right? You look at it, you go, yeah, it looks like integration by parts. You have some sort of, instead of a guess, it's kind of an educated guess. The same thing with these. It says, number one, if the series has the form, 1 over n to the p, it's p series, we know it's convergent, blah, blah, blah. We know about geometric. So it's kind of saying to you, look for p series, look for geometric right away. And then it keeps on going over things. Look at number 4. If you can see at a glance that the limit of the sequence doesn't go to infinity, then you'd be done, wouldn't you? That's what I've told y'all several times. If the limit of the sequence doesn't go to 0, does not go to 0, it diverges, right? So you want to look at that. 5, if the series is of the form, one of those forms, it's alternating, right? Then you can try the alternating series test. If you have factorials, things like that, then maybe the ratio test. Also the integral test. So they put a couple of examples here, and they tell you what how to go about them. But then at the back of the second page, there's 34 problems. And each of these 34 problems can have any of the tests from 8.2, 8.3, or 8.4. So they're all mixed up in here. And then the answers to those are actually the next few pages, page 4, 4, and 5. So they have all 33 problems worked. Well, not worked. I mean, they show some of the work, okay? They at least give you an idea of how to do each of those. Okay? This is a great review. What I would suggest you do, studying for this test for 8.2, 8.3, and 8.4, is to look at problems like this. I mean, because here you don't know what section you're in. You don't know if this is, you know what I'm saying? Like, you have no clue what's going to happen here, and that's the way the test is going to be. So that's a great place to start to review for the test. And I think when I sit down to make the test, I'm actually going to sit down and start with this. I'm going to look at these problems and go, okay, that looks pretty cool. Yeah. This is a good review. Yeah, y'all like reviews? This is a good review. Now, on the test, I'm going to allow you to have this strategies sheet. just that first page, okay? You can't have all these problems worked out. You can't write down on each of these things like what method you used. I expect you can use this completely virgin page, nothing written on it at all, okay? Just like this, torn off. You can use that on the test. You can use this on the test. That's that summary of the different tests that's printed in landscape sideways like that. You can have that. I said you could write on the back of that. Did I? I thought you can. I don't care. You can write on the back of that, and you can have one additional sheet, front and back, steps and procedures. No worked out problems. You can have any worked out problems written down anywhere to take this test. All right?
You have an extra one of those.
Extra. I do.
Yeah, Deb's worked out with, like,
You just got to be real careful. You got to be real careful because I mean, all of these series are, you know, if it's like n to the n over n factorial, like if you write out steps, you better not have like just b to the n b factorial, you know? Don't try and work a bunch of problems out and do it in some hieroglyphics code, whatever. I mean,
So is it 7 point something to?
okay, yeah, this is just chapter 8, all right? This is just chapter 8. I don't anticipate you seeing anything from 8.1. 8.1 was sequences, right? The only reason we talked about sequences is so that we could get to series. And when you look at series, you have to look at if the series, you look at inside and you say, does the sequence converge or diverge? So we're already kind of covering sequences by doing series. So it would just be 8, 2, 3, and 4. And then from chapter 7, 7.3 is shells, right? 7.4 is arc length. 7.5 is surface area. 7.6 is engineering applications, which is just the centroid problem.
All those? So 3, 4, 5, and 6? So
Mm-hmm.
4 problems.
Yeah.
Well, there's going to be 8 problems from.
It'll probably be about 8 problems from chapter 7 and about another, 6 to 8 maybe from here. Yep. And you'll have to do probably about half of them in class.
Doesn't matter which ones?
Doesn't matter, but on the integrals, I'm still just going to require, well, you know what? I don't know. I'm not going to lock myself down today. You might have to compute the integrals, but I'll keep them pretty clean, like powers and, stuff like that.
It's going to be like, 2 problems. Like you say, it's going to be 2 problems like of shells and all that. What about you just answer all of them and then we say 8?
Well, no, because here, this is a good question, okay, because I don't want anyone to walk in and get shocked by this. I'm going to have, if I have like from 7.3, I'll have 2 problems. 7.4, I'll have 2 problems. Okay, from those sections, you're going to have to show me at least one. So I'll be like, choose one of these, choose one of these, choose one of these. Once we get to chapter 8, it's just going to be, here's like 8 to 10 problems, do half of them. Okay, because what I don't want is you studying just chapter 7, coming in doing just the chapter 7 problems, and I'll do all chapter 8 at home. Yeah, it's a good question because I would hate for you to study that way and then show up and then be like, oh shit, this isn't the way I prepared. So, okay. We still have time, so I was going to work through some problems. You got to go or something? Okay. All right. That's okay if I keep going? Okay, thank you. All right, let's work on a few problems here.
Can we pick from the sheet?
Hmm?
Can we pick from the sheet?
No, I'm going to do some problems out of 8.4. Would you like me to do odd problems or do you want me to do even problems? What do y'all think? I'm doing 8.4 problems. I already put your homework assignment on the board right here. Do you want me to do problems from here or do you want me to do the even problems? Even? How many want me to do even? Okay, I'll do even. Did anybody wind up getting a solution manual in this class? You did? Is it helpful? Yes? So surprised that people have not gone out and got solution manuals. They cost money, yes.
What I did, which is less expensive, is I got a check account, and so that has a solution for my calc book, my organic book.
Wait, you got what?
Check. I've
check.com.
Check. Where you rent textbooks these days. If you don't
Hmm.
want them from the bookstore, you can rent them online.
Oh, cool. Awesome.
And you pay for an account, and it gives you like the answers to all of your books.
I got an email today from one of the faculty members that we were talking about like online courses. There's like this website they're advertising like let us take your course for you. Like you register and then they go take all the online course for you. You pay them.
How's that not academic dishonesty?
You're right. I know. So our college, our district is trying to get they're trying to get all of our online courses to be truly online where a person never has to come in face to face, which a lot of schools do.
A lot of the courses are like.
Yeah, but like our math classes, you have to come in and take a midterm and final face to face. So they're all like, "Well, that's not truly online." I said, "Well, how do I know anyone? How do I know anything about the person doing it?" So
I actually have combined many things.
you what?
There's one of the problems with online classes was people pay like these like Indian companies
Uh huh.
India, and they would just like do all their homework and quizzes.
Yeah, that's awesome, man.
For someone to test your quiz, they have to like check the IP address, make sure you can do like in college station. Like even if you're like in Houston, you won't allow you to log in.
Yep.
My ex did an online class and she had to have a camera with a mirror behind her so they could tell there was nothing else in the room.
Really? See, that's where it's headed, but that's way too much, Big Brother stuff and technology. It has to be in place, and they just need to do away with all the online stuff. It's a joke. It's convenient, but it's a joke. I mean, you can get a PhD online and do like nothing. Yeah, let's do some problems. All right, here we go. The question here, test this series for convergence or divergence. I like problems like this. These like test problems where I don't give you the sum, blah, blah, where you actually have to determine what the series is first, like write it down in its form. So what's happening with the numerator here? Well, this is alternating. Let's take care of that first. To create an alternating series starting with a positive, I need to take -1 raised to n plus 1, or I could do n minus 1, either way, right? Okay, now tell me about the fractions. Numerator is always 4, right? And the denominator is always n plus 6. Okay, so it's just going up by 1 each time. It's just going up by 1 each time, but it starts at 7. So if I plug in 1, I get 7, then 8, then 9, then 10. Y'all see that? Okay, what would you like to do here?
B of n plus 1. It's not how long.
So,
Make it absolute.
you want to look at the absolute value of it?
Yeah.
If the absolute value converges, then this converges, doesn't it? What's the absolute value of that thing?
Which would be 4 over n plus 6.
4 over n plus 6. What's 4 over n plus 6 look like?
What do you go over? Is there
4 over infinitely big number plus 6. So
Okay, so since y'all, I'm letting you guide me through this problem, all right? So you wanted me to do this. Absolute value of a sub n, right? And that absolute value is just 4 over n plus 6. Now, let me look at that as a series, right? And what I'm hoping for is that converges, right? Does it or not? Can you compare it to something? Let's look at the whoa. Let's look at the 4 over n plus 6. How can it be compared? Harmonic? Okay, 4 over n. Does 4 over n converge or diverge? That diverges, right? Which one of these is bigger? The one on the right's bigger? So that means that I can say that this term here, this is smaller than this, isn't it? And I know when I add all these up, it goes to what? It goes to infinity. That means that your sum over here goes to something less than or equal to infinity, which means what? It means you don't know anything. Well, but think about it, because if it converges, it's going to go to a number smaller than infinity, right? And if it diverges, it's going to go to infinity. And all that says is that, yeah, it's going to be infinity or something less. So that doesn't tell you anything.
He did it in red too, so.
Yeah, so that,
That's how we knew it.
no, no, that wasn't on purpose. That wasn't on purpose. I was just following you, and so. Now, so what we did first is we looked at the absolute value. Once we looked at the absolute value, we used comparison, but the comparison didn't give us any information.
Would you just go ahead and just use the ratio test on this?
You could try ratio test.
Yeah.
You want to try ratio?
That's what I would do. Because you already know your A sub n is 4 over n plus 6.
Let's do it in red. I'm going to do ratio then. I shouldn't have deleted all that. Let me see if I can get all that back.
Yeah, because your A sub n is the same.
No, I just want to move. I want to leave that there in case later someone wants to look at it. So this did not work. So now I'm going to do ratio test. I'm not doing ration. I'm not doing it in green because it's right. I want to take the limit as n goes to infinity of the absolute value of what? A sub n plus 1. What's a sub n plus 1? Yeah, and am I going to care about the negative? No, because I'm going to take absolute value. So it's really just going to be 4 over n plus 1 plus 6 times, now remember I said when I do the ratio test, the a sub 1 on the bottom, I flip it already. So it's going to become what? N plus 6 over 4. Which is limit n goes to infinity of, let me multiply across the top, 4n plus 24. Oh yeah, I can cancel the 4's. You want me to cancel the 4's? All right, all right. Sorry. Cancel the 4's. N plus 6 over n plus 7. Let n go to infinity. Infinity over infinity, L'Hopital. You get 1. What does the ratio test tell us when we get 1? We don't know anything. Yes. Alternating series test? Yeah, that's probably going to do it. This is the first problem in the section, and that was the first thing we learned. So let's try it. Let me try the alternating series test.
You always start with the most powerful thing you have, and then if you know it's not that.
Yeah, I like the ratio test. I mean, it's pretty good, huh?
You're gonna upload this tonight?
Yeah, I'll put all this out there. I'll put the video. I'm trying to upload the video tonight from my house. Yeah. Okay, alternating series test. What does the alternating series test say?
Take the absolute value and you look at the event.
You look at the part that's not the negative 1 squared or negative 1 to the power. And we call the b sub n. And for us in this problem, it's 4 over n plus 6, right? And what are the two things that we need for the alternating series test? B sub n plus 1 must be less than or equal to b sub n. And the second condition we need is the limit as n goes to infinity of b sub n equals 0. How about that second condition? I can do that almost just by looking, right? Look at this. Let n go to infinity. I'm done. Fixed over infinity. I'm done. This one is the one I need to show. So let me try that one. B sub n plus 1, we already said that was 1 over, or 4 over n plus 7, right? And the other one is 4 over n, 4 over n plus 6, which is true, right? Denominator on the left is bigger than the one on the right, and everything else is the same, so that is true. So what's the conclusion of the alternating series test. If both conditions are met,
Converges.
then it converges.
If it's greater than one or less than one.
It has to be equal to 0.
If what's then? If what's less than?
If it's less than one,
If what?
it converges.
No, no, no.
Greater than one.
This is the alternating series test. You're thinking ratio test or root test.
Plus one is less than the event.
Yeah.
Those two.
These two conditions have to be met. They are met. The series converges. So therefore, sum negative 1 to the n, whatever it was, 4 over n plus 6 converges. I don't know what it converges to, but it converges. All right, this one will go pretty quick. How about sum
Something test like.
n equals 1 to infinity?
They're all tests.
So I have a question for everyone. Assuming most of you hadn't seen series before, and we still have a long way to go when it comes to series. What do y'all think of it so far? I mean, compared to integrals and all that other stuff, like, how do you see it?
It's not as challenging yet.
I have no idea what we're doing. I hate this.
I think it's completely abstract to what we've done before, so it may be a little confusing.
I'm just trying to figure out what I tell my next Cal 2 class.
Well, that's what I'm saying. Like we go from like integrals and doing all integration by parts, and then you like it's like mass amounts of algebra that's like really simple, and it's like you're like up here, and then it's like drop down completely like.
Well, it's not drop down, so you gotta know which one to use.
But this is like
Who the hell do you think
this
you
is
are?
more like you have rules and you have to follow them. Like integration, like you have all those rules, but like you
Yeah.
have to.
Okay.
See, I knew why we were doing integration. This is just like.
Does the n equal 1? Are you going to be using n's as a test?
I may switch from n's to k's. Doesn't matter.
Oh, okay.
You should feel comfortable with both n's or k's.
The math part of it is
I
like
see what you're saying. Like you're trying to say like the procedure wise for
the math part of it is much simpler than with integration. Now the processes and everything like that may be the same,
Yeah.
but the like depth of how much math you need to know is a lot different.
Is it? But whenever I said like sequences and series, did you have any like inkling that this is what it was going to be? Like any sort of? Yeah. Okay. We still have a long way to go, but all right. Okay, so let's check this one out. Um,
alternating right away.
it is alternating. You could do alternating series test. What did we try last time? The first thing we tried was the absolute value, didn't we? Let's try the absolute value real quick. What does the absolute value of this thing do? What's the absolute value of a sub n? It's just 3n minus 1 over 2n plus 1. What's the limit as n goes to infinity of that? Yeah, L'Hopital gives you 3 halves.
So it doesn't equal 0, right?
It's greater than 1, yes. So, diverges,
Converges to 0.
converges, diverges.
Converges. Where's the sheet? If that converges, then
I'm not writing on this divergence.
This is the limit of the sequence, right? We're taking the limit as n goes to infinity of the absolute value of the sequence, and we're saying it goes to 1, right? What does that tell you? What's that?
inconclusive.
Isn't it converging to one then?
If it goes to 0,
Inconclusive.
it's inconclusive.
If it's greater, no.
Yeah, maybe it's.
If it doesn't equal 0. Isn't 3 halves the answer? It converges. Yeah.
3 halves is what the limit is. That's not what that adds up to be, though.
Isn't it converging?
You know, right? I mean, of course you know.
Yeah, no, I do, but think about what is happening to each. Look at each term. When you look at each one of these, forget the negative for a second. When you look at each one of these, right? The further out you go, they're getting closer to what number? 1, right? So, I mean, if I draw a graph, it looks something like this. It's going out towards 1, but it's asymptotic, right? Each term in the sequence. And then I'm adding them up, right? So I've got like something getting closer to 1. So I'm taking something close to 1, I'm adding on top of it something close to 1, and then close to 1, and then close to 1, right? Each time I'm stacking 1 on top of 1 on top of 1. And we said that would diverge, right? But this is alternating. Does the alternating change it though? Does it? I'm going to draw you. I'm going to draw you a picture. I can do it on here. Here's what the sequence is doing. If I just look at all those pieces of the sequence positive, if this is 1, it's getting closer and closer to 1, right? That's the absolute value. That's what's happening. If I add all those up, that should diverge, shouldn't it? That should diverge. Okay, now if I throw in the negatives, negative, then this is -1, right? It's getting closer to -1 here. Mm-hmm. So you go 1, then you take away 1, right? 1, then take away 1. 1, take away 1. Well, but each time you go out one more, you add it again, and then you go out again, and you subtract it again. What's happening is it just keeps on popping back and forth, and so it doesn't go to a specific number.
So you say it oscillates? That's it?
You say it diverges. The sum diverges. It's relying again back on the idea that if that limit doesn't go to 0, it's going to diverge. That was the nth term test, right? So let me go back to my page here. Here we go. So here's what we've got. I'm going to try and draw a conclusion here. Therefore, from here, it diverges. This was called the nth term test. If it doesn't go to 0, it diverges. If it goes to 0, you don't know anything. As long as it doesn't go to 0. Yeah. All right, let me see. 28, do we have time for another one?
This was an absolute value. Is it just used? Or is it just
Nth term on the absolute value. So that diverged. All right, let's look at the next. Let me give you something where you're not really ready for it. Like you don't know what it's going to be. All right. Test material. Test material. This will be our last example. We've got a factorial in there.
Ratio.
The strategies page says that if you see factorials to do what? Where is it? Number 6, series that involve factorials or other products, including constant raised to an nth power, are often conveniently tested using ratio test. Often. So let me try ratio here. So ratio test says I need to take the limit as n goes to infinity of the absolute value, right? Absolute value of a to the n plus 1. So I need to plug n plus 1 into this. Negative 10 to the n plus 1 over n plus 1 factorial. But then all over a sub n, but that's, remember, I flip it and do it already. So it'll be the n factorial over negative 10 to the n.
And then you pull off that.
Would it be negative 10? Well, now that I take an absolute value, I can throw out the negative, right? Because remember, negative 10 to the n is the same as negative 1 times 10 to the n, which is negative 1 to the n times 10 to the n, isn't it? Isn't that true? Negative 10 to the n is negative 1 times 10 to the n. Apply the power to each one, negative 1 to the n times 10 to the n. Take the absolute value of this, and you just get 10 to the n. So I'm going to replace them all with 10 to the n's. I'm also going to do something else. Instead of writing in the top left corner 10 to the n plus 1, I'm going to write 10 to the n times 10 all over, instead of n plus 1 factorial, n plus 1 peel off n factorial times n factorial over 10 to the n. Don't really need the absolute value anymore, but good cancellation here. So you have limit n goes to infinity of 10 over n plus 1. Yeah, you don't even need L'Hopital here. That just goes to 0. What is the conclusion from the ratio test if you have a limit that's less than 1? 0 is less than 1, right? It's absolutely convergent, which means that it is convergent, right? Which means that it is convergent. So ratio test was good on this one.
You have the other 10 because it's
What? I do what?
you have the other 10 because most time you have 10 n times 10. It's because of that one, right?
10, what? Yes, because of the n plus 1.
N plus 1.
Yep.
Okay. I'll back.
All right, I lied. How about I just set this one up? Maybe I'll just help you get started. 2/5 plus 2 times 6 over 5 times 8 plus 2 times 6 times 10 over 5 times 8 times 11 plus 2 times 6 times 10 times 14 over 5 times 8 times 11 times 14 plus, oh, this is a good problem. Talk about the convergence or divergence of this. Yeah, you have to figure out there's a pattern here. Do y'all notice anything?
Well, it's 3 by 4 on top and 3 on the bottom. So multiplying together.
What are we doing on the bottom each time here? We go 5, then we go 5 times 8. Then 5 times 8 times 11. Then 5 times 8 times 11 times 14. What's happening each time we go out? We get 3 more, right? We get 3 more? Bless you. What do y'all think? So when I start out with n equals 1, right? When n equals 1, how am I going to create 5? And then the next time create 5 times 8.
Would it be 2/5 times m plus 4 over m plus
Wait, say it again. Is it what?
2/5, 2 or 5 times m plus 4 over
Well, look at just the denominator for right now. I think it's a little bit too much to try and do close. On the bottom,
Because 3 times 2, oh,
Would you not?
you're squaring 3 and subtracting 1. Oh, no, you're
Would it
not.
be 5 plus 3 n? Because every time you're going up by that number, it's harmonic in its way. But it's 5 plus 1 times 3 is 8. And 5 times 3 times 2 is 6. Hold on. Yeah.
it's got to be a factorial because each time you go out, you're adding one more thing to multiply. Let me just, I think for this one, because time, right? We do have time here. Oh, wow.
5 minutes.
Okay,
It's just like warm up
3,
for a quiz.
3 times 1 minus 1 gets you 5.
try this. Let's see if you can come up with why it's this. Oh, in fact, hold on.
It's z minus 1.
The top,
3 and
if
plus
it,
2.
the next one would be, I'm trying to figure out where I can put this. Hold on, I'm running out of room. Let's say plus dot dot dot. I'm continuing. I'm looping around. Okay, plus. So what would it be? It'd be 2 times 6 times 10 times 14 times 5 times 8 times 11 times 14 times. So what would like the nth guy here be? What would the nth term here be? This is the first term here, the second term here, the third term here, the fourth term. I'm saying what would the nth term look like?
And factorial plus 2.
Makes me nuts.
Well, hold on.
That one.
Okay, so you start with 2.
I want to almost give this as a bonus now that I'm thinking about it. This is a good problem to just, because I picked an even problem, so I know you're not going to have the answer to it. Why don't we make this a bonus? I think it's good enough to make a bonus. What's that?
It wouldn't be a bonus for her.
Do you have, oh, you have the evens too? Oh, wow, that's good.
Everything and ever.
I have everything.
It's like her absolute convergence.
I am God.
Okay, well then maybe not.
Just switch it up.
4n minus 2 over 3n plus 2.
Oh yeah.
Oh yeah, that's
Keep it.
See, because if I start out, well, it's not factorial though, right? That's what's happening here. If I let n be 1, what do I get here? 5, right? n be 2, I'm going to get that one plus, what, 2, 6 plus 2 is 8?
We were trying to factorial.
So the last guy is this, right? That's what the last two factors would be, these two pieces.
You can L'Hopital rule those, right?
Yeah, but that's still only the end of it.
Oh, you need some.
What you would need to do here is a ratio test. Oh, I keep on saying ration. Ration. What's the limit as n goes to infinity of a sub n plus 1 over a sub n? So what would the n plus 1 look like? It would be all of this, right? But putting an n plus 1 in here, and then put that over all of this with n's. And then when you flip it, almost everything cancels except for the n pieces. Then you have to figure out with L'Hopital's rule what goes on. That's a tough one, but gives you an idea. I can't give a bonus now. Thanks, Pamela. Well, at least she's being honest, right? She could have not said anything and then been the only one with the answer. Okay, we have our test coming up Wednesday. Y'all